In this video, we're going to go over a theorem which says that a function is bijective if and only if it is invertible. And to prove this, we're going to need a theorem on surjectivity, injectivity, and composition of functions. If you haven't seen the proof of this theorem, I have a link in the description. Now, every time we have a theorem on a biconditional, I like to play a little game, which is to guess which implication is easier to prove and then try that one first. In this case, it's from right to left. So let's get on that. We're going to start with a function, which is invertible. So let f from a to b be an invertible. An invertible function, which means that there exists a function f inverse such that composed with f, it's going to give us the identity over b. Now our theorem here, the theorem C, says that when the composition is surjective, then the second function is surjective. But watch this. We have the identity function is bijective, which means that the composition f circle f inverse is also bijective. In particular, the composition is surjective, which means we're allowed to use our theorem C here. So since the composition of f circle f inverse, this right here is surjective, f is surjective as well, and that is by virtue of, let's put that in green, by virtue of theorem C. So all that's left is to show that f is injective, and then we would be able to conclude that f is bijective. Now, if we tried to use the same theorem, the theorem D on this composition, we'd only be able to show that f inverse is injective. We can't say, our theorem doesn't allow us to say anything about the injectivity of f. But when we switch the order of f and f inverse, it's still going to give us the identity function. So we can use the same argument. So let's do that. Likewise, f inverse composed with f, this will give us the identity over a, and this is injective because the identity function is injective. And now we're able to use the theorem D. Let me use another color. We can use the theorem D right here. So f is injective, and that is by virtue of the theorem D. All that's left is to conclude that f is bijective. Thus, f is bijective. Conversely, I think the converse is more difficult than the proof from right to left because it's not as obvious that we're allowed to use the arguments that we're about to use. So conversely, if f is bijective, we want to show that f is invertible, which means that it has an inverse, and we're going to define that inverse. We're going to construct it. So let g be a function that goes from b to a, and f is bijective, which means that it is a one-to-one correspondence between the two sets a and b. So it sends every element x in the domain to a unique element y, and every element y in the codomain has exactly one pre-image. This will allow us to define g in such a way that it takes y and maps it back to x. So from a to b, this would be f, and from b to a, this would be g. Now take the time to appreciate why we can only define a function g in such a way when f is bijective. Go over the definition of a function and take the time to understand this. This is very important. So we're going to define g to be the function the function which sends each element y that is in B to the unique element x that is in A, such that f of x is equal to y. So this definition simply says that the element x such that f of x is equal to y, well, we're defining g to be such that it takes that y and sends it back to x. Now, by construction of the function g, the way we defined it, we have g circle f is equal to the identity over A, and f circle g is equal to the identity over B. So I claim that g is the inverse of A, and we're going to show that. So indeed, that is the case. We're going to take an element x that is in A, and we're going to define y to be the image of x under F. So when we take g circle f of x, by definition of composition, this is equal to g of f of x. We want to show that this is equal to x. So g of f of x is equal to y. So this is g of y. And g sends y, the element y that is in B, to the unique x in A such that f of x is equal to y. So this g sends y back to x. We can do this in the opposite order as well. So let y be an element of B, and x be an element of A, such that f of x is equal to y. We're able to define such an x because f is surjective. It is bijective, so it is surjective. Now, when we take f circle g of x, of y, it's equal to f of g of y. And again, the definition of g says that we're sending y to the unique x such that f of x is equal to y. So it sends it back to this element x. So we have f of x, and f of x is equal to y. So this is equal to y. And this shows that our two compositions are identity functions. So this allows us to conclude that g is the inverse of f, and we can put our little square of satisfaction.